Some space missions capture attention because they ask a question too big to ignore. Can humans learn to live beyond Earth without pretending space is easy? NASA's Artemis program is built around that question. Its goal is not only to visit the moon again, but to practice the skills. A future deep space civilization would need launching powerful rockets, carrying crews far from home, operating near the moon, and eventually working on the lunar surface for longer than a brief flag and footprint stay. The moon is close in cosmic terms, but it is still a brutal place. There is no air to breathe, no weather to soften the ground, and no quick rescue. If a spacecraft has a serious problem, every system has to be tested with patience because the distance is short compared with Mars, but enormous compared with ordinary human life. What is known is that Artemis has already begun proving hardware in space, including an uncrewed flight around the moon. What remains uncertain is the exact rhythm of the next crewed steps. Spaceflight schedules change because engineers would rather find problems on Earth than discover them with astronauts aboard. That is why the mission matters. Artemis is not just nostalgia for Apollo. It is a rehearsal for staying. The question is whether humans can build a reliable path from Earth to lunar orbit to the surface and eventually farther out. Scientists care because the moon preserves ancient clues about the solar system. Engineers care because the moon is a testing ground. Viewers care because it turns space exploration from a single heroic leap into a long, careful return. The memorable takeaway is simple. The moon is not the finish line. It is the nearest place where humanity can practice becoming a spacefaring species. And that leads naturally to the next kind of mission. One that does not carry people, but goes where humans cannot yet survive. Imagine sending a spacecraft to an ocean you cannot see around a world you cannot safely orbit for long. That is the strange challenge behind NASA's Europa Clipper, a mission headed for Jupiter's moon. Europa. Europa looks frozen from the outside, but evidence from earlier spacecraft suggests a global ocean may exist beneath its icy shell. If that ocean is real, it could contain more water than all of Earth's oceans combined. The mission is not going there to announce alien life. That would be far beyond what the evidence can support. Instead, Europa. Clipper is designed to ask a more careful question. Does Europa have the ingredients that could make an environment habitable? Habitable does not mean inhabited. It means the basic conditions might be present, such as liquid water, useful chemistry, and a source of energy. On Earth, life follows water almost everywhere. So when scientists find a possible hidden ocean beyond Earth, they pay attention. The hard part is Jupiter itself. The giant planet is surrounded by intense radiation that can damage electronics. Europa Clipper will not simply park beside Europa and stay there. Its plan is to loop around Jupiter and make many flybys of the moon, gathering data in repeated passes, while limiting time in the harshest zones. What is known is that Europa is one of the strongest places in our solar system to study habitability. What is uncertain is the thickness of the ice, the chemistry of the ocean, and whether material from below ever reaches the surface in a way a spacecraft can sample from afar. The mission matters because it turns a distant moon into a test of one of humanity's biggest questions. Could life-friendly worlds be common even where sunlight is weak? The takeaway is this: some of the most important places in space may be hidden under ice, and after worlds, the next mission's story is about light itself. The most powerful space missions do not always land on worlds. Some simply open a new kind of eye. The James Webb Space Telescope is one of those missions. Instead of traveling to a planet or moon, it sits far from Earth and studies the universe in infrared light. That is light our eyes cannot see, but it is incredibly useful in space because it can pass through some dusty regions and reveal objects that are too cool, too faint, or too stretched by cosmic expansion for ordinary visible light to show clearly Webb matters, because it changed the questions scientists can ask. It can study the birthplaces of stars, the atmospheres of some planets around other suns and galaxies, whose light began traveling when the universe was very young. It does not give instant final answers. It gives better evidence. One reason Webb feels so fascinating is that it is both a time machine and a chemistry tool. When it studies a very distant galaxy, it is seeing ancient light. When it studies an exoplanet atmosphere, it can search for the fingerprints of molecules. But fingerprints are not the same as a full story. Signals can be faint. Atmospheres are complex. Early galaxies are still being debated. What is known is that Webb has expanded astronomy's reach. It has revealed surprising details in young galaxies, dusty star-forming regions and worlds beyond our solar system. What is uncertain is how some of those discoveries will fit into the bigger picture after years of follow-up observations. This is why missions like Webb shape what comes next. They help scientists choose future targets, design better telescopes, and decide which mysteries deserve the next generation of spacecraft. The takeaway is simple. Exploration is not only about going farther, it is also about seeing deeper, from the moon to an icy ocean world, to ancient starlight space. Missions are teaching us how to ask better questions.